Ever thought about trying to measure something that goes on forever? I mean, it sounds like a complete paradox, doesn't it? Well, today, we're going to do exactly that. We're diving into the pretty fascinating world of improper integrals, a seriously powerful tool in calculus that lets us, quite literally, measure the infinite.
So let's start with this question right here, because it really gets to the heart of the matter. You're looking at a shape that just keeps going and going and going, and we're asking if its area could actually be a finite number. I know, your intuition is probably screaming, no way, that's impossible. But you're about to see that calculus has a really surprising answer for us.
All right, here's our game plan. We'll kick things off by understanding what makes an integral improper in the first place. Then we'll introduce the key tool we need to solve them, the limit. After that, we'll get our hands dirty with some examples, and then I'll show you a really cool shortcut at the end. Okay, so first things first, what does it even mean for a definite integral to be improper? Well, it basically just means we've hit a kind of problem that our standard integration rules can't handle right out of the box. Let's break down the two main types you're going to run into. So here's the formal definition, but don't let it scare you. An improper integral is just a definite integral that we can't solve with our usual methods. And this happens for one of two big reasons. Either the area we're measuring goes on forever, or the function itself blows up to infinity somewhere in that area. This slide gives us a perfect breakdown. On the left, you've got type 1. Think of this as the area stretching out sideways to infinity. On the right, you've got type 2, where the area is stretching upwards to infinity because of an asymptote. See? Both are infinity problems, just going in different directions, and we're going to tackle both. So how in the world do we handle these two types of infinite problems? Well, it turns out we have one incredibly powerful, really elegant tool that solves both of them. And that tool is the limit. Let's see exactly how this thing works. This 5-step process right here is our secret weapon. Now look closely at step 2. That's the magic trick. We temporarily swap out the problem, whether it's infinity or an asymptote, with a nice normal variable. Let's call it t. This turns our improper integral into a regular one that we already know how to solve. Then, in the final step, we use a limit to sneak back up on that problem spot and see what happens. So once you evaluate that final limit, you're only going to get one of two results. If you get a finite number, like 5 or 1 or pi, the integral converges. And that means, incredibly, our infinite shape has a measurable area. But if the limit runs off to infinity, or just doesn't exist, we say the integral diverges. That means the area is truly infinitely large. All right, enough theory. Let's actually put this toolkit into practice. We're going to walk through 3 examples, starting with the very one that created our paradox, just to see how this 5-step process really works. And here it is, our first challenge, the integral of 1 over x squared from 1 all the way out to infinity. This is a classic type 1 improper integral. So let's fire up our 5-step plan and solve this thing. Let's break this down. First, we replace infinity with t and set up our limit. Next, we integrate x to the negative 2, which gives us negative x to the negative 1, or just negative 1 over x. Finally, we plug in our bounds t and 1. Now for the crucial part, what's the limit of negative 1 over t as t heads towards infinity? Well, think about it. If you divide 1 by a billion or a trillion or a gazillion, that fraction gets so small it's practically 0. And there it is. That first term just vanishes to 0, leaving us with a final, beautifully simple answer of exactly 1. I mean, how cool is that? This is a fantastic result. We've just mathematically proven that a shape that is infinitely long can have a totally finite measurable area. This isn't just some math trick, it's the power of calculus to bring precision to the concept of infinity. Okay, for our next trick, let's make a tiny change. Instead of 1 over x squared, we'll look at just 1 over x. This function also gets smaller and smaller as x gets bigger. So what do you think? Is its area also going to converge? We're going to run the exact same playbook. Set up the limit, find the antiderivative, but here's the crucial difference. The integral of 1 over x is the natural log of x. So when we go to evaluate the limit, we're really asking what happens to the natural log of t as t shoots off to infinity. Well, the natural log function, even though it grows pretty slowly, it grows without any bound. It just keeps on climbing forever. So the limit is infinity, which means our integral diverges. This tells us something really important. Even though the curve of 1 over x times looks a lot like 1 over x squared, it just doesn't shrink to 0 fast enough. The area underneath it is truly infinite. Okay, we've tackled a couple of type 1 problems. Let's switch gears and look at a type 2. Now, in this case, our interval is finite, just from 0 to 1. But the problem is our function itself, which has a vertical asymptote at x equals 0. The function just blows up to infinity there. The process here is almost identical. We replace the problem value, in this case 0, with t and set up our limit. Now, see that little plus sign next to the 0? That's really important. It just means we're approaching 0 from the right side, from inside our interval. Then we integrate and we evaluate. And what do we get? The limit of the square root of t as t goes to 0 is just 0, leaving us with a final answer of 2. It's amazing. This infinitely tall region, all squeezed in between 0 and 1, has a perfectly finite area. Okay, you have done the hard work. You've mastered the full process of using limits, so now it's time for a reward. A shortcut. We're going to look at a special rule for a very common family of integrals, those that look like 1 over x to some power. This is going to save you a ton of time. This right here is the p-integral test, and it is a game changer. For integrals that look like 1 over x to the power p, from 1 to infinity, the rule is incredibly simple. Just look at the power, p. If p is strictly greater than 1, the integral converges. If p is less than or equal to 1, it diverges. That's it. It's that simple. And this one single rule perfectly explains our first two results. For 1 over x squared, p was 2, which is greater than 1, so it converged. For 1 over x, p was 1, which is not greater than 1, so it diverged. With this test, you can nail these common problems in a flash, no limits required. So what's the big takeaway here? We've seen that what seems like an impossible paradox, measuring an infinite shape, is actually no match for calculus. By systematically using limits, we can tame infinity and get concrete, real answers. And this isn't just a mathematical party trick. This technique is fundamental in fields like probability, physics, and engineering. It opens up a whole new universe of problems we can now solve. The possibilities are quite literally endless.